So in today's lesson, we're going to be learning about how elements on the periodic table combine to form compounds together. And so before we get to that, I want to remind you of a few details relating to the periodic table. I want to remind you that first off, that the elements on the periodic table are divided by the staircase line around here. And what that does is it reminds you that all of the elements to the left of the staircase are all metals, and all the elements to the right of that staircase line are all considered to be nonmetals. And so we're going to be looking at, well, what happens when metals combine with metals? What happens when metals combine with nonmetals? And what's going on when we have two nonmetals that are combining to form compounds? So hopefully while you're watching this, you have your skeleton note in front of you and you're able to fill in some of the details as we move through this. So the first thing I want to talk about is, well, what happens if you have a metal atom combining with a metal atom, right? Well, we did touch on this earlier on in the unit, but metals will combine with other metals to form something that we call an alloy. And it's really not a new compound because technically no bonds are going to be formed between the different metal atoms. A good example of this is brass, or steel actually. So brass is made up of a little bit zinc and mostly copper, and it looks sort of like this right here. And if we were to zoom in at what's going on within this structure here, this brass structure, what we would see is we would see individual copper atoms and mixed in with individual zinc atoms. So it's really not much different than, say, taking salt and dissolving it in water and then forming a single phase solution. But there's no actual bonds that are occurring there. The only difference is that in an alloy, we're talking about metal and metal atoms, and we're also talking about solids that are mixing. So that's, if you were to be asked, well, what's going on when a metal mixes with a metal? Well, you would say it forms an alloy. So I also think before we move on to talk about metals and nonmetal compounds and nonmetal compounds, that we just take a look at the periodic table and some of the trends that we've discussed earlier in this unit. So the first is, well, we can tell based on the position of an element in terms of which group it's in on the periodic table, that tells us how many valence or outer electrons it will have. So for example, if we were to examine the Bohr-Rutherford diagrams of all of the alkali metals, right? So that's them right here. Here's our alkali metals. If we were to draw the Bohr-Rutherford diagrams, we would see that what they all have in common is that they all have one valence or outer electron, right? And so even though I haven't drawn the Bohr-Rutherford diagram for, let's say, for instance, cesium down here, I know that I can expect or predict it to have one valence electron. And so on and so forth, right? So if I move along and I look at beryllium and magnesium, they're in the alkali earth metal group right here. And I would also be able to predict that any element in that group has two valence electrons. And so the trend continues with this next group over here predicting to have three valence electrons. And then the group beginning with carbon on top, four valence electrons. Nitrogen, I'm running out of room here, but nitrogen and all the elements below it would have five valence electrons, as I can see in this Bohr-Rutherford diagram. And then following along with the halogens over here, having seven valence electrons, and my noble gases all having a full outer shell. And so if I break this down, I'm looking at all of the metallic elements. And I know that an element will be stable or happy when its outer shell is full. And it seems to me that the metal atoms, right, all have less than 4 electrons in their outer shell. And so because of that, they'll be much more likely to want to lose electrons. Whereas if I look at the flip side, at the nonmetals over here, the reactive nonmetals, they all have more than 4 electrons in their outer shell, and so they're more likely to want to gain electrons. Now, of course, carbon and all the elements below it are a bit of an exception because they have 4 electrons in their valence shell and are just as likely to gain or lose. So let's look at this a little bit more closely. So as we just talked about, metals on the left-hand side of the periodic table, they have these outer electrons. So here's sodium with its 1, here's magnesium with its 1, or with 2 rather, and aluminum with 3. So all of these metals have these extra electrons that they'd like to lose in order to become stable. But we have the nonmetals on the other side of the periodic table that all have more than 4 electrons, and so in their outer shell, and so they're more likely to want to take them. And that's exactly what happens when you have a metal atom reacting with a nonmetal atom. The metal atoms, we'll see, grabbing their electrons and then donating them to the nonmetals that need them for their full outer shell. Now, it's important for you to remember that when an electron is given away, you're giving away a negative charge. And so as a result of that, the element that is donating its electron then becomes positively charged, because then it has all of a sudden 1 more proton in its nucleus compared to its number of electrons. Now on the flip side, these electrons, as we mentioned, they're negatively charged, and so anything that's going to gain an electron is suddenly going to have more negative charges in comparison to the number of protons or positive charges in the nucleus. And so what's going to happen here? Well, we're going to end up with a situation where we have atoms or ions rather, and these ions are of opposite charge. So my cation, the positively charged ion, is going to be attracted to my anion, the negatively charged ion, right? And so they're going to want to come together. That's going to be a super strong force of attraction, and that's actually the force that keeps these metals and nonmetals together. And these, as you may remember, are called ionic bonds. Okay, so again, just to remind you, an ionic bond is formed when an electron is given away by a metal and is accepted by a nonmetal. So in other words, the electrons are transferred from the metal to the nonmetal, and that forms cations and anions, and that's what we call an ionic compound. So let me take you through an example of one type of question you may be asked. So in this question, I'm asking you to predict the formula, the chemical formula for the compound formed between lithium and oxygen. And so right off the bat, I know that lithium and oxygen are going to form an ionic compound, because lithium is a metal found on the left-hand side of the periodic table, and oxygen is a nonmetal. And so given that, I'm going to take a look at the Bohr-Rutherford diagram for lithium. So this is lithium, and I know that because it has 3 protons in its nucleus, and the periodic table tells me that lithium has an atomic number of 3. So lithium, as we can see, has this electron, this lone electron in its outer shell that it's not going to be too happy about having, and it's going to want to get rid of it. And I look over here at oxygen, and oxygen, it looks like it has 6 electrons in its outer shell, and so it's going to need 2 more. So lithium can gladly donate 1 of its electrons away, but it doesn't have another electron that it would want to give away. So here's how we handle this situation. So I want you to remember that an atom is really, really small, and so chances are, if you have lithium around, you have more than 1 atom that's available there. And so we know, and some of you may have predicted this already, we know that lithium is going to want to give 1 of its electrons away to oxygen. But oxygen's not stable. It's not happy yet, even though lithium is happy. And so what needs to happen is oxygen's going to do its best to also help another lithium atom out. And so lithium is going to donate another lithium atom, a separate one is going to donate a single electron to oxygen. And what this does is it allows us to predict what the formula will be when lithium reacts with oxygen. So as I can see, I have 2 lithiums needed to neutralize 1 oxygen atom, and so that tells me that the formula for the reaction between lithium and oxygen, the formula that results from the combination of these atoms is going to be Li2, representing the 2 lithium atoms, and then O. That's a messy O, but there we go. All right. So what I'd like you to do is I'd like you to take a minute just on the side, and we'll take this up as a class. What I'd like you to do is I'd like you to tell me what the formula will be for the ionic compound if aluminum were to react with, I'm going to say, sulfur. Okay, and so we've talked about metals and metals, they make alloys. We've talked about metals and nonmetals. Well, the metals donate electrons to the nonmetals. But what about when we take nonmetals and try to react them with other nonmetals? Well, here's the thing. And I'm going to use fluorine as an example, but I could have used other elements. The problem with metal or two nonmetals coming together is that neither one of them really wants to part with electrons. Fluorine here, as I've drawn it, has 7 valence electrons, and so all atoms of fluorine would also have 7 valence electrons. Neither one of these is going to want to give up any of their electrons, but they both want to become stable. They both want to become happy. And so here's what happens. They actually end up sharing electrons. So imagine this. What I'm drawing here is I'm going to draw and pretend that this is how they're sharing, but I'll get a little bit more specific about the details in a little bit. So if they're sharing that 1 valence electron, that one outer electron, it's kind of like this fluorine on the right has 1, 2, 3, 4, 5, 6, 7, and now 8 electrons. So it's going to be happy, right? And then if I look at this fluorine over here on the left, it also has 1, 2, 3, 4, 5, 6, 7 of its own electrons, plus 1 that it's sharing, which also gives it 8. So everybody is happy. Now this thing that we formed by the sharing of electrons, that is what we call a covalent bond. A covalent bond. And so let's look at this in a little bit more depth. So this is how you would typically see what I drew above in a nice diagram, where you can see that now it's almost like their outer shells or their outer orbits are overlapping so that they can share these electrons. So that, you know, really this blue electron from the fluorine on the right becomes part of the black fluorines on the left. And so as I said, this sharing right here is what we call a covalent bond. So if I were to ask you, well, where is the bond? You would want to say, well, this is where the bond is right here. This is one covalent bond. Okay? And that's really how molecules formed, right? They formed because of covalent bonding. So let's look at some more examples of this. So let's look carefully at an example of a water molecule. Well, the formula H2O tells me that there needs to be 2 hydrogens and 1 oxygen to make a whole water molecule. So if we were to draw the Bohr-Rutherford diagram for hydrogen, we would see that hydrogen has this lone electron in its valence shell that it wants to get rid of to become stable. But we have 2 of them because the formula says H2. So each of them wants to get rid of their electrons. And oxygen has 6 outer or valence electrons. They're not drawing the inner ones here just for simplicity's sake, so we're focusing on the valence electrons. But we can see that oxygen has 6 valence electrons and needs 2. Well, that works out great in terms of sharing. So hydrogen is going to share its electron with oxygen. And that's happening twice because I have 2 hydrogen atoms. And so in this case, everybody is satisfied. As it turns out, oxygen is not powerful enough to pull that electron away from hydrogen, and so sharing is what works best for them in this situation to make a nice stable water molecule. So I have 2 tasks for you. The first one is I want you to draw the Bohr-Rutherford diagram for carbon and for 2 oxygens, and I want you to predict how it is that carbon and oxygen atoms are going to come together to form a molecule of CO2. Now again, when I look at this, I can tell that CO2 has to form covalent bonds and share electrons because I see that carbon and oxygen are both nonmetals, and so both nonmetals are not going to want to transfer electrons, they're going to want to just simply share. Once you've done that, just to see where your understanding is, I want you to fill in the table that's in your note that looks like this. So that describes, well, what's going on with an ionic bond in terms of the electrons versus a covalent bond, and what types of elements typically form an ionic bond and which come together to form a covalent bond. Do your best, try to work through this. If you're struggling, we will take it up as a class. And then if you can, then what I'd like you to do is to move on to the questions at the bottom of the sheet as well. Here they are. And if time permits and you want to see some of this in a little bit more depth, then here are 2 suggested videos that will help you out.